I hope you watched the video with the soap film. Maybe a little dramatic music you set to it. I don't know. But you saw the different colors. I'm not going to get into all the details about the little bubbles you saw and the way it seemed to drain down at the bottom, or even why it looks black at the top near the end. What I'm mostly interested in right now is simply the rainbow effect that you see, and why you see some colors in some places and other colors in other places on that soap film. That's what we're going to talk about. We can get the other stuff later on if you want to, but let's just keep with the fact that you saw that rainbow effect and why certain colors show up at certain locations and why other colors show up at different locations. So let's take a cross section of that soap film. Okay. And I think in the video for sure what they had was a white incandescent light shining on it. But let's say for the sake of our discussion that we're going to take ourselves a laser. Remember, a laser has coherent light, all the same wavelength, all the waves in step with each other. Okay? And we're going to shine a laser at the soap film. And here is our disembodied floating eyeball, the observer. Okay, looking at the whole thing. Well, here's what's going to happen, right? The ray, the incident ray, is going to strike the surface. This is, again, the soap. Okay. So out here is air on this side. On the other side of the soap also is air. Okay. Well, some of that light's going to reflect back into our eyeball, right? And so we say, hi, we see light. That's how we see the film, is by reflecting the light. That's how you see everything, whether it's your dog or whether it's, you know, a doorway, whatever it is, you see it because the light's reflected off of it. I mean, there are exceptions, right? You don't see the sun because light's reflected off of it, or a candle flame. But in this case, you see the soap film because light reflects back off of it. Now, in reality, right, there is a, this is a reflection. So we've got the normal there. We've got our angle of incidence, theta 1, our angle of reflection, theta 1 prime, right? And then what happens is some light is going to be refracted in, right? And some of that light is going to be reflected off the back of the soap. We saw this in one of our labs, our refraction lab. Did we even do that one? I can't remember anymore. It's all blur. Anyway, some light's going to move into it. We talked about this when we talked about reflection and refraction way back when, before all this COVID nonsense started. And then some of that's going to refract back out. Okay. So here is our angle of refraction right there. Okay. One thing we need to do for this example, we need to remember that we need to say that theta 1, theta 1 prime, and theta 2 are all small, essentially 0 degrees. So we're really using very small angles here. Now, this doesn't change the essence of the physics we're doing. It simply makes our calculations simpler. Okay, we can deal with throwing in angles, non-zero angles later on, but just know that all these angles I've drawn here are just super small. Okay, super small. That's going to be our approximation. Approximately 0. All right. So we see two rays. 1 and 2. The first ray reflected directly off the front of the soap film and then entered our eye. That's ray number 1. The second ray has traveled further. Okay? It has refracted into the soap film, reflected off the back surface of the soap film, and then refracted back out into the air. Okay? So we have two different rays hitting our retina. Okay? I've drawn them separately, but in reality these angles are very small, so they're right on top of each other. Okay, I draw them separately just to keep track of them. Okay, so one ray has traveled further than the other. That is, there is, as there was before, a path length difference delta R2 minus R1. One ray has traveled further than the other. We last saw path length difference back with Young's double slit experiments. It's the same idea here. Two rays are adding up on your retina, but one of them has traveled further than the other. The difference in the two paths is delta. R2 minus R1, absolute value, is always considered to be a positive number. Okay. But what is the path length difference in this case? How much further has 2 traveled than 1? Well, it's traveled through the soap and back. So if we call the thickness of the soap film T, it's kind of odd. Lowercase t in this case is not time, it's thickness. But this is universal. I've never seen any other symbol used. So there it is. Little t is the thickness of the soap film. So ray 2 has traveled further than ray 1. And because these angles are very small, we can approximate and say that thickness t is related to that path length difference. In other words, the distance that 2 traveled further, it went from the front of the film to the back of the film, and then it went from the back of the film to the front of the film. So this business here, the stuff, the path taken by ray 2 inside the soap film is the path length difference, and that is equal to 2t. So for thin film interference, the path length difference is not what it was before. It was d sine theta back in the Young's double slit experiment. But here, the path length difference is equal to twice the thickness of the soap film, because ray 2 has traveled 1t, 2t further than ray 1. Notice they're coherent because they came from the same original ray. Okay, the incident ray, 1 and 2 both have their origin in the same ray, and that ray is coherent. All the waves are stepping together. Okay. So these two waves combine on our retina in the same way that our rays 1 and 2 combined on the screen in Young's double slit experiment. Okay. So, based on what we talked about in the last video, in video 10, if these two waves are out of step with each other, there will be destructive interference. If these two waves are in step with each other, there will be constructive interference. If they're in step, they'll be constructive. If they're out of step with each other, they'll be destructive. Okay? What that means is that if the path length difference is equal to m lambda, that is, if ray 2 had to travel m lambda, where m is equal to 1, 2, 3. If ray 2 traveled m lambda further than ray 1, then the wave of ray 2 has been shifted an integral number of wavelengths relative to ray 1. And like I took with that red wave earlier a couple of videos ago, if I shift that red wave a whole wavelength relative to the one that wasn't pink, that wasn't red, we'll get constructive interference. So this is condition for constructive interference. Actually, let me do that differently. I don't want to put a box around, because boxes, when I write boxes around things, that means that's the answer. But we need to adjust it. We'll need to adjust this a little bit. Oh, fudge. We're hitting 10 minutes here. So, if 2t equals m lambda, then wave 2 will be back in step with wave 1. Ray 2 will be back in step with ray 1. Okay, so that is constructive. Because if I took the pink wave and shifted it one wavelength or two wavelengths, we got back to constructive interference. However, if 2t equals m plus 1/2 lambda, then wave 2 will be out of step perfectly with wave 1, and we'll have destructive interference. Okay. If constructive interference is happening, then we get a bright spot. We can see the light in this case. If destructive interference is happening, then both waves cancel each other out and we see nothing at all. Okay, now I'm going to put dotted line around this because this is not the answer. Okay. What we're trying to find ultimately is under what conditions we get constructive interference and what conditions we have destructive interference. That's what we're looking for. This looks right, but it's not. Okay, and we need to fix it two different ways. We need to adjust it for the two different topics that we've already discussed. Okay, we need to talk a little bit about phase shifts. We need to talk a little bit about the change of wavelength when light goes through a medium. The two topics of the last couple of videos. We need to take this apparent answer and tweak it, okay, to make it right. The dotted line around it means that it's not right. It's not the final answer. Okay, we're going to adjust it two ways. Coming up.